me-design.com, and that will be available within a few days after this presentation. The Pavement ME Design Task Force provides guidance and oversight for the maintenance, support, and enhancement of the Pavement ME Design software. Our members are first Ryan Fragapane is our AASHTO project manager. Again, I'm Clark Morrison. Hari Nair is the vice chair. Our other members are Patrick Birrell from Ohio DOT, Kumar Dave with Indiana DOT, Felix Doucette with the Quebec Ministry of Transportation, Dulce Feldman with the California DOT, Ian Risch with Georgia DOT, Suzanne Chan from Ontario Ministry of Transportation is our liaison to the Transportation Association of Canada, and Tom Yu is our FHWA liaison. Now, just a few housekeeping items. Phones are being muted. Also, please post your questions in the Q&A box, and this can be accessed by clicking on the WebEx Q&A button. The presenters will answer all questions at the end of the webinar as time permits, and questions not answered because of time will be responded to separately, and the question and answers will also be posted on the me-design.com website with the presentation. With that, I'll turn it over to our presenter, Wouter Brink.
Thank you, Clark, and welcome everyone. Just to expand upon some of the items that Clark just mentioned for the Q&A, it's sometimes kind of tough to find where they are, so we have these slides here. So if you have any issues with the webinar, so this is sound-related issues or you can't see anything, when you hover over to the top of your screen, you'll see a little drop-down box that shows up that'll have basically your audio settings, participants, some of the chat. You should be able to see a chat, and then also the Q&A. If you do have any audio issues and the sound and are using the computer audio, the dial-in option is a possibility, so feel free to dial in, and then you'd be able to hear the audio. For the Q&A, so to ask a question, make sure you go to the Q&A box. It'll allow you to answer your questions. It'll go to all the panelists, and we can answer some of those as we go throughout the webinar. And if you have questions trying to find where that is, feel free to add that to the chat. But we try to reiterate that the Q&A is boxes where we'll answer all the questions. And to see the presentation in full screen, so this is also in the drop-down box at the top, you'll see view and then fit in viewer. So it's kind of different ways to look at the sizing of your screen and presentation. Okay, so first we'll start with the poll question. So I'll get this started. Open poll. And please respond to the poll. Okay, so about 82% so far. We'll give it a couple more seconds. Okay, so we'll close the poll. Thank you for your responses. Continue on. So I want to go over just a few items before we get started. So a prerequisite for this webinar is that you do have some prior experience with the Payment ME design software, design of rigid payments for new and rigid rehabilitation, and then also the rigid payment distress performance prediction models. So most of this presentation is all related to rigid payments. So some of the learning outcomes, at the end of this webinar, you'll be able to identify the changes to the rigid payment distress prediction models after the integration of the NCHRP 1-51 results, which is slab interface, incorporating slab interface friction between the PCC and base layers underneath. List the new inputs required for the JPCP cracking model and where they are located in the UP Payment ME Design version 3 user interface. Also list the updated global calibration coefficients and factors for rigid payment distress prediction models, and evaluate the goodness of fit statistics and revise standard deviation of the residual error relationships for each distress model. For the webinar today is split into several different parts. So part 1, I'll go over the NCHRP 1-51 model integration, the new inputs, what we had, some of the assumptions, what we had to complete to integrate the model with the existing Payment ME design framework. Part 2 is the global recalibration of the rigid models, which includes both JPCP and CRCP payments. And then part 3 is just the summary and closing comments. And then part 4, it'll be the question and answer session. So as we we'll start with part 1 here. The most important note here is that the NCHRP 1-51 models and the global recalibration was done for Payment ME Design version 3. So this is the web application. All the new items are included. So as you can see here, the new enhancements that are not in version 2.6 of the desktop version compared to the web application. So that's the new NCHRP 1-51 models, rigid payment global recalibration. The models were calibrated using MERA2 climate data and is now the default climate set for rigid payments. And the direct MERA2 climate data download and integration is only available in the web application. So for part 1, I'll go over an additional outline here. So I'll go over the summary of the 1-51 product, what we used for the integration process, and then also some impact of some of these changes on the predicted performance. So first I want to mention this, the integration process is based on the research study completed, which is NCHRP 1-51, incorporating slab and underlying layer interactions. So the full title is Incorporating Slab Underlying Layer Interaction into the Concrete Pavement Analysis Procedure. It was completed in 2017, University of Minnesota, and the authors and researchers for the completed the work is Lev Kazanovich and Derek Tompkins. So what the overall summary of the research really expands upon the existing rigid payment models that are already in Payment ME. Lev was involved in an original recalibration or model development from 1-37A, 1-40D, and really developed the updated models based on the existing JPCP cracking model, and then proposed additional enhancements that can improve the predictions for rigid payments. So the first one is a modified JPCP transfer cracking model, proposed a revised default base layer LTE values that are built into the defaulting model, and then also revised base friction coefficients for CRCP punch-outs. So to go over the proposed revisions for JPCP cracking model specifically, it incorporates interface friction between the PCC slab and the underlying base layers. It can be granular bases, cement-treated bases, asphalt bases, and it modifies the effective thickness calculation and how to incorporate for the friction between those layers. Then also incorporated or suggested a revised built-in curling equation where the top and bottom of the slab results in different built-in curl. And then also a revised temperature linearization procedure and accumulation of linear and non-linear temperature gradients. So what that kind of comes down to is the interface friction between the slab and underlying layers. In Pavement ME currently, or in the version 2.6 in the older models, basically it was able to model either a fully bonded slab or a fully unbonded slab. And now with the NCHRP 151 research results, it basically modifies or determines a partial bond between the slab and base. So it looks at the effective thickness of your fully unbonded slab and your fully bonded slab, or slab fully bonded with the base layers, and then based on the friction value, it predicts a modified effective thickness to account for that partial bond between the two layers. And that deteriorates over a monthly basis or stays fairly constant. As you can see here, we have that's your effective thickness and a function of a non-dimensional friction factor. And so as the friction factor increases, you're closer to a fully bonded slab compared to a lower friction value where it's fully unbonded. To go over the new inputs, so in general, it uses almost the exact same inputs as Pavement ME, except for a few extras. And that was one of the purposes, or one of the goals from the authors of NCHRP 151 to help with the implementation process. One of the items is the concrete characteristic length. So this was added as a new input, and it's kind of tied to the maximum aggregate size. It's to account for some of the nonlinear stress distributions throughout the slab and on the apparent strength. So this value, a value of 2.5 was recommended, and as a base value. Then the next one was a top surface strength reduction factor, which this parameter is already included in Pavement ME, so it did not need, it's not a direct input by the user, but it's in the model itself. Two new parameters here to account for the built-in curling based on the top and bottom of the slab. So basically it adjusts the user input value and then kind of accounts for the top of the maximum gradients between the top and bottom of the slab. And this is a new input parameter that is added to the calibration factors. Then for the next one is your initial non-dimensional slab-based friction factor L star. So this is the main user-defined input that is used to account for the friction between the slab and the base layers. So you have your full slip basic values, very small, and then a full bond is to 100 to 1,000. Like the higher values are for fully bonded. So this is a new input parameter. Its default behavior is typically based on base type. It can be. And then the last one here is the friction degradation parameter CF. A value of 300 was determined by the NCHRP 151 authors as the default value. And same with the L star of 0.01, and that was determined during the calibration process. Just to show you how the friction-related equations are implemented within the model. So the L star is your initial user-defined non-dimensional friction factor, and then it calculates a initial monthly friction value at the start of the analysis period. Then it's a function, and your L star and your friction parameter is a function of the thickness of your PCC layers, the thickness of the base, and the modulus of your PCC and base layer. The next part is an estimated and inferred monthly friction. This is where the CF parameter comes into play. So it looks at your min and max constant strain temperatures and then divides it by your friction degradation parameter. So this gives you how quickly your friction factor is going to reduce over time. Then the revised built-in curling. So if this is the adjusted or proposed revision to just using a single value for your delta T input to model the difference between your curling and warping moisture related items within the top and bottom of the slab. And as you where now it'll use the input value that is entered by the user currently, and which is a very sensitive parameter, and it's usually because it's become a calibration parameter. And then you have your A and B coefficients, which I mentioned and showed earlier, the 6 and the 20, and then it's a function of your base and PCC layer modulus and thickness. So you have your delta T is your built-in curl, and if it's a date, it changes between the daytime and nighttime built-in curling values. And you see the delta day results in the more positive component, while the delta T night represents the more negative component. From a fatigue damage standpoint, these equations will look very familiar, except for a few additions. So the current, or the V2.6 cracking model really shows your damage as a function of your allowable N, which is your C1 calibration factor, your C2 calibration factor, your modulus of rupture, divided by the total stress of your different loading loading configurations that apply stress at the different conditions. Now the addition here is to account for your constant stress and your nonlinear stress, and then also your total stress. So this is the new part that is included within the 151 analysis modules. And as you can see, the C1 coefficients, C1 and C2 are still similar to the current prediction models. And the CC factor is calibration constant to account for your curling stresses. If this value is 0, everything kind of boils back down to just the original past model for your fatigue damage. So some of the limitation assumptions, models in the 151 report, it really applies to new JPCP designs. And the one nice assumption, or the good thing, is that it uses the existing pavement ME design inputs and outputs for, you have traffic, it directly uses the exact same information for your single axle, tandem, tridem, quad axles, uses the same climatic inputs for PCC thermal gradients and data, and also the material inputs. So from that perspective, it was very similar and based on the existing framework within pavement ME. So I want to go over the proposed revisions to the JPCP faulting. There were no direct changes to model source code, so it was the main recommendations were revised default initial LTE values for the different base types, from granular bases, stabilized materials, soil cement, cement stabilized, and asphalt bases. So these values were already included in pavement ME. It was just adjusting some of these LTE values. So as you see here, the proposed, here's the LTE for the total joint. So it's a component of your dowel LTE, your aggregate, purely aggregate interlock, and your LTE based on your base type. So as you see, the LTE for the asphalt bases, the NCHRP recommended value is 40%, and compared to the 30% that was proposed from the 137A results in the original faulting model development. And for LTP granular basis, it remains the same. And then the other one that changed is the cement treated bases was reduced from 40 to 30. The proposed changes to the CRCP punch-out models, there were no actual source code recommended changes. It was a revision to the default slab base initial friction factors is, sorry, this is a typo here, is the friction factor based on the granular stabilized base materials. So you can see here we have the friction value for cement treated bases. It was 8.9. It is now recommended as a value of 6. The friction value for asphalt bases was adjusted from 7.5 to 8, and then no changes for the granular bases. And this is only as an initial starting point. The pavement ME design, or the MEPDG manual of practice, also provides different friction, recommended friction values for different base types. It has a broader range, and this is just for when you create a new design within pavement ME and you specify a base type, these values will be used as default. And then the user can change them as needed. Okay, from that, I want to briefly go over how we integrated all of these, the models themselves into pavement ME. There were different source code, or different languages, and we had to work with the NCHRP authors to make sure we interpret the results appropriately and incorporate them into the current existing framework for pavement ME. So the steps here, the first one was to verify the findings with the NCHRP authors. So we did a review of the source code, a review of the report, matched the different equations with the source code. Then we implemented the models within the pavement ME design framework. Then performed detailed testing, looked at the results compared to the original source code versus the integrated source code, and the inputs and outputs to make sure the results are the same. And then also that led to the global recalibration of the cracking, faulting, and punch-out models. So from a detailed review, these included code similarities, differences in languages, so Fortran versus C#. One example here too is the any potential typos that we had to verify with the NCHRP 151 authors, how to address those, any discrepancies between the report versus the source code and which one was correct. So we went through that process in the beginning to make sure that we're following what the intent of the NCHRP results were, and limit the amount of issues or items that could potentially cause further issues down the line. So integration tasks. So we have the first one was the transliteration of the source code. So the software team transliterated the Fortran code to C#, which meant that we had to verify the unity of the results between the Fortran application and the C#. So even if there were typos in the Fortran, those were also in the C# at that point in time in the beginning, just to make sure we have a one-to-one comparison between the two, and then we can move forward with making the necessary adjustments and incorporating it into the overall ME design framework. So some of the typos were fixed. We worked with the NCHRP 151 authors, so we worked with Lev Kazanovich to make sure that all of those are corrected and the equations are updated and documented. There were also some analysis runtime improvements based on how the stress linearization procedure that was implemented. So that reduced the overall runtime of the rigid quite significantly. And that also occurred during some of the integration tasks. So to continue here, also the next step was to look at the user interface updates. Where do the new inputs go within the interface? What new calibration factors need to be added? So that includes the DGPX file themselves, where in the analysis run process would these go, how are they incorporated? And then the last part was looking at the testing, the new inputs. So for JPCP cracking, that was the effect of your L star, CF, and your A value and the different base types. You're looking at the JPCP faulting. It's more related to default LTE value and for the different base types, and then CRCP also the initial friction factor that is used. And then proceeded to global recalibration. So where are these properties within the user interface? So when you are in the web application, if you're familiar with the desktop, you'll notice that the screen here on the left, the screenshot here is very similar to what you see in the desktop application as well. So it goes into your general information, your performance criteria inputs, your traffic, your climate, structure, maintenance strategy, calibration coefficients, and then the design properties based on which design you have selected. So in design properties, you'll also see other items like your joint spacing, your erodibility factors, if it's a wide slab, and so on. And then the new inputs here is the PCC base interaction or interface friction inputs. So you'll see here your L star value, what gets entered, your friction degradation factor, your CF, and your characteristic length of 2.5. So the default values are based on the global calibration, and then if you have user-defined values, then you can actually make those user-defined. For the calibration-related inputs, so there's a couple items. So you have your calibration. There's a new pill within the calibration factors for JPCP friction. This is where you have your friction damage degradation factor. Curling and other stresses, there's a CC factor, so you can actually turn off the interface friction if you would like. And then also the built-in curl A and B parameters. Now for JPCP faulting, you won't see any new user interface changes. Most of the default LTE values were it's coded within the software, so no direct changes there from a user interface perspective. And then for the punch-out model, what you'll see is once you select your layers, you build your layer, you go over to your piece or design properties, which is similar to where they were before. And if you have an asphalt base, the value will default to the 7.5, and the CGB bases would default to your new value. Okay, just to give a couple examples here, I looked at, for this example, it's kind of the impact of your L star non-dimensional friction factor to the CF parameter, how changes in that value affect your predicted cracking for granular bases. So you can see here, for granular bases, even if you go from, all full 0.001, which is your fully unbonded, all the way to fully bonded, there's not much of a change between those values, which should be expected. And then for the degradation factor as well, also very minor changes for a large range of friction values or friction degradation factor values. Now, when you see a much bigger difference when you look at and compare the cement treated bases, see here for a few thousand value, so it's like fully bonded for the entire, well, fully bonded initial friction factor. You can see it's the lowest amount of predicted cracking. Then it increases from there. So basically you're fully unbonded to fully bonded. And the default value of 0.1 is kind of right in the middle there. Similarly for the degradation, the low value of 800 or the highest value gives you the best prediction there. And it affects the rate of how quickly the friction value changes. And similar for asphalt basis, you can see a similar trend as for CTB. The magnitude is just slightly less compared to the CTB, but the trends remain the same. Okay, so we'll go to the next poll question here. So as I finish that part, I went through pretty quickly. Yeah, let's start here. Open the poll. I will give it about another 30 seconds before closing. Okay. Go ahead and close it. It'll still allow who just started it to finish. thank you for your responses. So now with part one complete, the models were integrated, built into the payment ME design framework, the different modules, and then required to perform the global recalibration of the original models. This is part two of my presentation. And the outline for this part is the introduction to calibration process. I'll just go over some of the items we looked at. Then the calibration of the JPCP transfer functions, and also that's your cracking, faulting, and IRI, and then the CRCP transfer functions for punch outs and IRI. So first, I want to answer why perform global recalibration. So the main goal here was to recalibrate the models because they have not been recalibrated since 2013. That was back it's version 2.2 of the software. The calibration sections had a lot more distress data available, especially most of them were closer to 20 plus years now. Also needed to recalibrate the models with using the MERIT-2 climate data. This is one benefit there is it now pavement ME design uses a single climate data set, so it's all the global models are calibrated to the MERIT climate. Agencies can still use their own climate if that is what they would like. And the last item here is the integration of NCHRP 1-51 slab-based interface friction. Introduce new inputs and changes to the different models, so that which required at least to look at the differences between the old coefficients and determine if a global recalibration is needed. Okay. So when we move to the global calibration of the rigid models, I'll go over the details for transverse cracking, transverse joint faulting, and JPCP IRI, and go through some of the items that we found throughout calibrating both or all of these different models. First, I'll start with the available sections. So this here shows the number of sections we had available for the global calibration. This includes mostly LTPP sites distributed throughout the country. So you have there's 258 sections LTPP and then 16 non-LTPP, which is mostly just the min-row sections and phase one or two, I believe. So those sections are well represented. They are distributed throughout the country, different climate zones. You'll see a few in Ontario, also a couple others in Canada as well. And these are distributed here by the different climate zones. So purple, you have your wet non-freeze, wet freeze, dry freeze, and your dry non-freeze here in the Southwest. So if we start looking at the age distribution for these pavement sections, so I looked at the last distress point before any major rehab was done. So we didn't want to include measured distress points and ages that were rehabilitated because it'll change the actual predicted or the measured performance, reset all the different distresses. So I looked at where our maximum age occurred. So I mean, you can see, I mean, most of the 95 out of those sections were between 20 and 25 years. We have sections up to 45 years or greater than 45 years. So it's a very good distribution compared to some of the back when 2013. So I think that helps with capturing some of the late stage deterioration that occur, especially from a a cracking and faulting perspective. When we look at the JPCP sections for the different base types, the majority of them were granular bases, so that also includes sections that were directly on a subgrade. There's 10 lime-treated sections, then we have 85 cement-treated and asphalt, 68 asphalt sections. So they're well distributed. A lot of these were SBS2 sections for the different agencies, also several GPS sites as well. We look at the different joint spacings, so they're kind of splits between your constant joint spacings and random joint spacings, and then we look at what those mean or typical spacings are. So I mean, the vast majority of your sections, 148 of them, are basically 14 foot, and these are all the SBS2s, several of the GPS sites, and then you also have several others that are quite long. I mean, you have 23 sites that are about 19, 20 feet. Very few sections towards the 24, 23, and your 30-foot sections there. And then when you look at the random joint spacing, there's a lot less of those, but most of them had around an average joint spacing about 17, 18 feet. Look at our coefficient of thermal expansion, also well distributed, but it's mostly towards the lower CTE values. So you have between your 4 and 4.5, typically your limestones, good quality, low thermal expansive aggregates. Then you have 4.5 to 5, getting closer to your dolomites, and then the more highly expansive aggregates. It's also fairly well distributed, so you have quite a few of these, some sections with very high coefficient thermal expansion values. And these are the updated values reported in the LTPP database. The previous calibration corrected some of the CTE method from basically the version 2 or earlier versions that were calibrated. And we want to look at the PCC slab thickness distribution. So you can see most of the slabs, most of them are between 7 and 12 inches. Then we have a few we have 2 sections that are basically 6 or so, between 6 and 7, and then very few that are in the 12 to 15 range. The majority of them were about with the 8, 9 range, and 9 and 10. So I mean, it's all distributed within 7 and 12 inches. The next item I want to kind of highlight here is the average number of sections with the different climate regions, and also the temperature and precipitation information. This actually doesn't show the precipitation, but we have the mean annual air temperature from Humera climate data versus the ground-based weather stations for the different climate zones. So you can see, I mean, they're fairly close, there will be differences, but it is expected to kind of see that the average value should fall within the same region of values. So I mean, even for the Mera, it was slightly lower, but it's slightly lower for almost all of them. That's kind of an interesting finding there, but for the most part, it compares okay based on the climate zones themselves. Now, if we go into the transfer cracking model calibration. First, I compared the measured transfer cracking, what that distribution looks like. Split those up by joint spacing as well, so constant joints versus random joints, and then also looked at the number of distress surveys. And here on the x-axis, we have the measured transfer cracking for those sections and the frequency of those bins. So you can see for constant joint spacing, I mean, the majority of slabs or measured transverse cracking is between 0 and 5%. Then you have a significant drop-off where you get to 5 to 10, and then continue to decrease over at the higher levels of cracking. So, I mean, for the most part, probably 95% of your data is within the first 0 to 30%. And for the random joint spacing sections, you have a lot less sections for one, but also you have the number of magnitude between your distresses are fairly similar to what you're seeing from a distribution in the constant joint spacing. So I mean, most of them were 0 to 5, and the next were kind of significantly less. Now for the number of distress surveys, so there's a bigger difference between from previous calibrations. So I mean, if you look at the average number of distress surveys and data points for the JPCP sections, I mean, it's between 9 and 12 distress surveys. Most of them are collected every year. I know for the SBS2s, that's the goal. Well, I mean, it's quite good. The majority, I mean, the ones that had 21 distress surveys, I think those are the ones that are still in service. The Arizona sections, the SBS2s there, have a lot of distress data points, so that's good compared to some of the earlier calibrations where there's only about 2 or 3. Now we're looking at the initial verification. So after 151 was integrated into the overall pavement ME design framework and the analysis modules, we compared the existing version 2.6 calibration coefficient, so that's 0.52 and then negative 2.71. How does that predict for those sections? So we have the predicted transverse slab cracking on the x-axis or y-axis, and then you have our measured. So I mean, overall, I mean, it predicts quite well. There is some bias. Your standard error over your standard deviation of your measured is 0.42 is pretty good. And then if we look at the damage prediction, so this is with the new linearization procedures, the nonlinear temperatures. It captures your damage overall quite well. If we look at our residual error, so I mean that it's quite scattered. We have some of these sections early on which showed a lot of measured distress, but not necessarily a lot of predicted. So predicted minus measured. So overall, we used 173 sections, 1,600 data points. You got a R square 0.82. It's pretty good. SESY 0.42, and bias is less than 1%. Slabs cracked. Your slope of 0.79, and then your standard error is about 5. Then we looked at the hypothesis test. They still, it's not. So the only one that passed, or we can't say that it's different than 0, is the intercept. So it's the 0.17, and then your slope is statistically different than 1, but it's expected. And it depends on how many data points you have as well. So now, when we look at the calibration itself, we looked at different combinations. We looked to see if there's a bias between different inputs, different base types. We looked at the different L star and CF values. We looked at constant joints versus random joints because there seemed to be a difference there. But when we looked at the base type dependent coefficients, we didn't find that there was a need to differentiate or specify calibration coefficients specific to the different base types. We looked in that comparison, we looked at the standard error, we looked at the SESY, we looked at our hypothesis tests, we looked at an analysis of variance to see which inputs affected the overall residual error the most, and also the measured stress. For the ALSTAR and CF, we ran a significant combination, basically a matrix of values, and then looked at the standard error, the bias in general, which combinations had the lowest bias versus the highest. So from that analysis, we found that the recommended defaults actually showed the most reasonable predictions. So it corresponds to what the NCHRP 151 authors. And then between the constant joints and random joints, we looked at the difference in the bias there. Initially, we used the constant joint spacing sections to kind of come up with a ballpark estimate for the C4 and C5 calibration factors, and then we added those sections back in to kind of look at the overall reliability and the standard deviation of the residual error to make sure that we can capture both types of designs. Now, when we look at the final calibrated model, here we have our predicted measured and predicted versus measured and your predicted damage. So what you can see, the difference between the previous slides, the slope or the values increase slightly, and it's very similar. The SESY reduced, your bias is a little lower, plus your standard error also reduced, and the coefficients are not significantly different. So I mean, you have a C4 went from 0. What was it? 0. I'll have to look, and I have it on the next slide here. And then the C5 also changed slightly. Now the goodness of fit here, let me go over these. Slightly different, and from a hypothesis standpoint, intercept also is still not significantly different than 0. The pairwise comparison for the mean difference between the predicted and measured data, that is, the p-value is closer to 0.05 compared to the previous, just using the other global coefficients, the previous global coefficients. And then the slope is still different than 1, but it is better than the just using the old coefficients. So here, this shows you your direct comparison. So we have the verification, which uses the version 2.6 calibration coefficients for C4 and C5, and also the friction 151 friction model. You can see here, the improvement. So R squared is very similar. Your SESY is almost identical to the bias reduced. So you have it's about less than 0.5%. And then your slope increased. Adjusted R squared is about very little, and then the SE is almost identical. Now, from a hypothesis standpoint, your calibration value of 0.02 is closer to 0.005 or 0.05, and overall, I think the recalibrate coefficients provide a slightly better model compared to just using the old calibration coefficients. Now, from a reliability standpoint, updated standard deviation of your residual errors relationship was derived. So this goes into your reliability. And here's the new relationship. Here's your bins for your different distress types, 0 to 2, what your average values and your standard deviation of those represent. And to compare to the previous pavement ME design V2.6, you see the differences here is highlighted. The standard error equation is slightly different. And then that gets added to your design reliability. So next, I'll go to the transverse joint faulting. From a faulting perspective, we focused here on doweled versus undoweled to see how different the distresses are and the magnitude of those. What you'll notice here is for doweled pavements, I mean, the majority of the data is between 0 and 0.5, and we look at these two bins here. So you don't have a lot of, for doweled pavements, the magnitude of faulting is not significant, it's not very high. Now you compare that to your undoweled sections where it's a much wider distribution. So you get faulting values that are range between 0 and probably all the way up to 0.25 inches. So, and then you have a couple sections here with very high faulting. Then if we look at the number of distress surveys similar to cracking, you have most of the sections, you have between 6 and 8, it's probably the most, but then also, I mean, you have some sections that really are towards the 20-year design period, or at 20 years old, well, 20 distress surveys, so that could be much broader age, depending on if they actually collected on every year. But every section, I mean, between 8 and 10, it's a good distribution of the stress points per location or per site. Okay, so just to kind of give an overview of your faulting model and what coefficients are being changed. So the red items, the red coefficients here are basically the calibration coefficients. So what you'll see here is your fault max 0, which is the initial maximum faulting. It's calculated right before it actually goes into analysis modules. Based on your deflection data for your curling, well, you're curling within the structure. And then you have your C1, 2, C5, which affects your erodibility and ultimately your base type. You also have the C6, which affects the entire quantity of this equation. Now the C1 and C2 is affects your basically from your frost perspective, and C1 and C2 goes directly into this initial fault max 0. Then once you have your initial fault or initial maximum faulting, it goes through the iteration by month. Now it calculates your monthly maximum faulting using the previous month plus your current month's predicted values, and the C7 really affects your differential energy, and differential energy is kind of tied to your dowels, your LTE, and those calculations. So I mean, C7 really affects how your dowels are impacted, and then C6 here really affects your overall erodibility portion plus how much and your base type. Then your faulting increment, so that's a change in faulting from a month-to-month basis, is a function of your C3-4, which is your C3 and C4 coefficients, and that's your maximum faulting plus minus your faulting increment, and then multiply also by the differential energy. And then overall, it calculates your cumulative faulting over your entire design life. So for verification purposes, so we have predicted versus measured. Kind of see, I mean, it's quite scattered, some over, some under. But I mean, overall, it's not bad. So I mean, your standard error is pretty low because of just the magnitude of these the faulting values. You have your bias, which is also very low because you see basically your over predictions and under predictions really cancel each other out. But I mean, from this perspective, I mean, we had 1,100 points, and this is from the V2.6 coefficients. Here's the statistics results. Kind of see we have the SCSY is not very good. You want this to be definitely under 1, plus it's the lower the better. Bias is pretty low, slope's okay. Your SEE is pretty low, but that's because you have very low faulting magnitude of predictions themselves. The pairwise t-test did show there's not statistically different than 0, while the other two are, but this is also an effect of your sample size. Now, if we look for your effects within coefficients, so what you'll see is I look at your C1. Basically, this shifts the initial maximum faulting up or down, so increasing and decreasing the value. C3, that really shifts your incremental faulting up and down. You have your C6, kind of increases and decreases the effect of your different base types because it corresponds to that erodibility input. And then also you have your C7, which is kind of your multiplier on your differential energy, and this is kind of where you can affect or change some of the effects of the dowels. After the calibration, what you'll notice is some of these items decrease that were over predicting or under because you had higher predictions were decreased. Your over predictions were reduced and your under predictions were increased. Your overall magnitude of the residual error, the bands here are much less compared to, say, up here you have quite a few sections between the 0.1 and 0.2, and now everything's pretty much within negative 0.1 and negative 0.1. When we compared the statistics, so I mean the R-square is still not very good, but it's better. They're actually these were more sections because this is from the previous calibration itself, so they didn't have some of the additional distress measurements. SCSY reduced quite a bit when you look at all of the pavement sections. Bias is, I mean, the difference between 0.01 and 0.009. I mean, it's still very low. Yes, it is higher. Slope also slightly reduced, but the R-squared and your SEE is lower compared to the previous. I mean, it's very close, but I think it's still it's an improvement, especially when we look at the subgrade or the different base types. I mean, we did look to calculate the statistics for each one, but there was the CTB and granular bases and asphalt bases, but there wasn't enough to suggest different coefficients for different base types. Now, from a standard deviation of residual error, derive new updated equation and fit the exponential function to it. And it's similar to the previous calibration, but with updated data and the result standard deviation or residual. So this captures kind of the deviance between when you have higher predicted values, your standard error increases. That kind of corresponds to what you're seeing here. So you capture that variability. Okay, now changes in coefficients. So as you see here, we have your C1, which went from, so that affects your initial maximum faulting, so it shifts it up and down. We have your C3 also, basically affects that overall magnitude. Then we have C6 or C7. And we ran a combination of different values of C1, C3, C5, and then select the ones that had the lowest bias and the lowest standard error, as well as the SE, SY. And you see here we have the updated faulting relationship for your standard error, standard deviation, and residual error. Now for JPCP IRI, now we have a lot of data available for IRI. A lot of these sections had a lot of IRI measurements, which is great. Now, if we look at just similar to what we did for faulting, constant joint spacing, or I think it was cracking, constant joint spacing, random joint spacing, and then by base type, you can kind of see what the overall magnitudes are and where the data is kind of falling. So you have your constant joint spacing. I mean, I would say the majority of the sections were between 75 and 100, 100 and 125, and then you get quite a few data points around 150 and greater. Now for random joint spacing, similar. It's a very similar trend. And then if we look at the asphalt bases, cement treated bases, granular and lime treated, we don't have a lot of lime treated sections, but overall, I mean, most of them had quite high IRI. Let's see. I mean, your cement treated bases had the higher IRI, especially if we look at the number of data points within the 125 and 150 inch per mile range. So for the IRI, we performed the calibration after performing the transverse cracking and joint faulting calibration, because the predicted values are used directly in the IRI model. So you have your cracking and faulting values need to be representative of what you're seeing in the field, and then we adjusted the J1, J2, J3, J4 coefficients accordingly. So if you look at the IRI verification, I mean, the overall IRI model is actually predicted quite well. I mean, we have a few sections that are above and below, but in general, once it's calibrated, once the cracking and faulting models are calibrated, it did okay. So most of them are scattered here around the line of equality. And then if we look at the error itself, I mean, most of it is scattered around the 0. We do have some sections that have a lot of either under or over prediction. And that can be a factor of many different things. We looked at what is the cracking and faulting within those sites. We looked at, are there other distresses? What does the spalling look like? Were there other types of issues that are not accounted for within pavement ME? So those, we try to eliminate some of those sections that had kind of abnormal performance in those situations. When we look at the hypothesis tests and the goodness of fit, I mean, overall, the bias itself is negative 4.14 inch per mile, so that's very, very low. Slope's okay. The standard error is about 18 inch per mile. And I mean, even though all the p-values were not significantly different than where they are significantly different, we have to look at the practical significance of these two. So I'll mention that next. Now, when we look at the updated calibration coefficients, you can see like most of those data points kind of drop down. The overall magnitude of your residual error is much less. Everything's between, let's see, on a maximum of 50 versus negative 50, 50. But most of the majority of them are scattered around 0 here. So I think that overall it is an improvement. And we look at the R squared increased slightly. We have our SESY slightly lower. It's pretty good still. Bias was reduced slightly. I mean, there's probably not a big difference between those two. Slope reduced slightly, but I think that's okay because the standard error also reduced. Now for our p-values, I mean, as you can see, all of these are significantly different than they all fail. But from a practical significant standpoint, I think the models are predicting quite well, because the difference between a 4 inch per mile is not significant. I don't think it can be IRI can be measured to that low a value. So that's one where I think these are acceptable. The one item that hasn't been updated for quite a while is the standard deviation of residual errors for the IRI equation. This was not an editable value in previous versions of the software. It really should be based on your local calibration. So in version 3.0, that is doable. So now you can derive your standard error residual error relationship for IRI. And this is the case also for CRCP. When we look at the coefficient differences, so J1, J2, J3, J4, so you have your different impacts here. The effect of your J1 is cracking, spalling. J3 is your faulting. So and J4 is your site factor. So site factor increased, but when we plotted the residual error versus the individual components, and try to eliminate any bias there, and that's one of the main reasons for these coefficients themselves and their impact on your predicted IRI. And just to kind of show you some examples here, we have our JPCP with the symmetry to bases. So this is for the same exact section. So we have our cracking, we have our faulting, and we have our IRI. So you can kind of see the prediction here. For symmetry to bases, I think the inclusion of the slab base interface friction really helped. Didn't need to adjust the built-in curling calibration factor or built-in curling factor as much. So the majority of these sections use the default value of -10, and then the adjustments to the model themselves that really helped capture some of the differences in predictions for symmetry to bases. Now if we look at faulting here, this one didn't have a lot of faulting, so it kind of still predicts pretty low. When you look at IRI, most of this IRI is likely contribution from the cracking itself. So I mean, we have quite a bit of cracking in this section, so you can kind of see how the model predicts for IRI. Now here's a section for granular base. So we have this is in 27, I think it's Minnesota. B2.6 predicted a lot of cracking with the calibrated model for 151, closer to reality, closer to the measure values. Faulting also over-predicted. The new faulting model is slightly better, but it's still kind of over. But the magnitudes of this section in particular is very low. Now for your IRI, similar here. Actually captures okay. Once you get to the later years, it kind of increases, and that's like a function of the cracking itself, plus also the high transverse joint faulting predictions here, because that gets multiplied by the number of joints. Now for an asphalt base, so I can see for version 2.6 of the software, I'm almost for asphalt bases, it predicted 0 cracking. Now for the calibrated 151, it does predict some. It's closer to the measure values. Now we're seeing here for faulting, it's more representative. The original calibration probably only had a few of these data points when it was calibrated back then. Now we have quite a few more points. Same thing for your IRI. It captured it quite well. And the increase of your IRI here is likely as a function of what is occurring here for your cracking. There might be other distresses involved, even though faulting is low. So the measure data might not, some of the measured items might not be well accounted for within pavement ME. But overall, I mean, especially for the initial stage, it's pretty good. Now, if we move over to the CRCP, we have our punch outs and CRCP IRI. Just one sec. Our CRCP sections, there's not as many compared to JPCP. We have 78 LTPP sites and then 34 non-LTPP. And they're scattered mostly, as you expect. Illinois builds a lot of CRCP, Texas has a lot of CRCP, and then they're kind of scattered throughout the eastern part of the U.S., slightly less on the West Coast. Many of the sections are between 20 and 35 years old, so quite a good distribution, so you can capture some of this long-term performance. Most of the CRCP sections had asphalt-treated bases compared to your cement-treated, granular bases, lime-treated. Thickness, almost the majority of sections had thickness between 8 and 9 inches. And then almost all of them captured between the 7 and 11 inches. Here for your marginal rupture, I didn't show these for JPCP cracking or the JPCP sections, but between 650 and 850 is your input values for marginal rupture at the kind of time of construction. These were backcast to the time of when these were constructed. Climate data, similar to what we showed for your JPCP sections. This includes the precipitation. So on average, here it's for dry freeze, it's a few sections with only 6 sections there. The average mean air temperature was a couple degrees higher than the ground-based. But the one thing to remember here is your ground-based stations might not have all of a 30-year period of hourly data. For the CRCP sites too, it wasn't consistent. Sometimes it was, here we have lower, your MERA was lower average compared to your ground-based. Here you have higher MERA, lower ground-based. But wet non-freeze, they're almost pretty much identical. Average precipitation, I think MERA captures more on average, it has higher precipitation values. For the dry freeze, I mean, it's still pretty low. Dry non-freeze is closer. And this is likely due to some of the way the ground-based stations reported precipitation itself, but also there's more data available. But yeah, for the wet freeze section, there's quite a big difference. We look at so now we move into punch outs. Basically, the majority of the punch outs per mile, it's really between 0 and about 75, and then you have some higher punch out values. We looked at some of these sections that are very, very high punch outs. I looked at the actual distress sheets from LTPP, and it's really like some of them are isolated sections where there's a punch out almost every foot, every couple feet. So every 2-3 feet there was a punch out, and then that would span for almost 500, 600 feet. 100 feet. Yeah, it wasn't the whole section, about 500 feet. But we looked into all it, and that's kind of why we're seeing a final calibration set versus all the measured data points. Yeah, because I mean, if you look at the magnitudes here, it's basically majority of 0 to 450, and then you can see some where the punch outs per mile are 1,500 and more. Now, if we look at the number of distress surveys between LTPP and non-LTPP, so most of the non-LTPP sites had kind of 1, 2, 3 distress surveys, while comparing the LTPP, which had more. Still quite a few between 0 and 1 distress point. So we focus more on the ones that had additional more distress surveys compared to just 1. Now, if we look at the measure versus predicted, so this is with the initial verification, we kind of see it's fairly scattered. The predicted distress is never greater than about 150 feet per mile, or punch outs per mile, while the measure values can range between 0 and 400 for a lot of these sections. Now, if we look at the damage plot itself, predicted damage versus your measured punch outs, you can kind of see there's a few of these outlier sections that really could control your design, but then here when you get to the end of the design period, well, it starts with the transfer function from before, kind of see how it starts accumulating more damage and measure cracking right around 0.01, 0.1 damage index values. So this is kind of where we focused on, and then you also see the one section or a couple sections which increases later on. When we split these out by base type, we looked at your asphalt treated bases, your cement treated, granular. Granular bases predicted quite well. Now we look at the lime treated. There's a couple of these outlier sections that we found. We try to look at their specific stresses. Then same thing with cement treated and asphalt. We look at the residual errors. I kind of see it's a few sections that are scattered, but overall most of them are around 0, with a few that are significant. Look at the overall bias here is -10 punch outs per mile, so that's very high. R-squid's not great, or it's terrible. SCSY about 0.9. It's less than 1, but it's still not very good. And your standard error of the estimate is very high, 45 inches per mile. Then our hypothesis tests also fail. So we're recommending calibration here, and we looked at the calibration itself. The model and transfer function, the old coefficient for the asymptote was about 100, 107. So we kind of adjusted that value. So now you can kind of see the adjusted coefficients. It predicts well for the kind of lower damage values. Well, we're seeing still low punch out predictions between 0 and 75. And then it also, once it starts getting a lot of damage, it'll increase, and we capture that with adjusting the asymptote value for CRCP for the transfer function. Now the coefficients were developed without those high punch out sections, but they were added back in when we looked at the reliability itself. So once the calibrated model, what you see is there's a few less data points because of those sections that were really controlling your calibration itself. You have your SCSY, which is much lower. Your bias is almost 0, so that's a significant reduction or improvement. Our slope is almost 1, and then also the standard error is still really high, but it kind of, once punch outs start to occur, you're going to see quite a bit of them. That's one of the things that really showed up in the distress charts or distress maps that I looked at. Once we look at the hypothesis test, you can see that none of these are different than the null hypothesis. So we kind of accept the new global calibration coefficients. And we look at the standard error. So we have derived new coefficients here. You can kind of see that second point. It's fairly high, and that's when we added back in some of those sections that were a little higher, but to capture some of that variability. We look at the overall coefficients, which you'll see here is the C3 coefficient, the asymptote, is 1760, so it's quite high, but that kind of translates to about a punch out every 2 feet, 2-3 feet. So it's kind of the upper limit of that prediction. And then accordingly, you can see the C4 and C5 also had to be adjusted to make sure that the transfer function kind of matches what we're seeing from a measured and predicted performance standpoint. And the adjustments here for your standard error, it is higher compared to what you're seeing before because the variability within those sections are quite high. We look at the CRCP IRI, so move to that. We have our measurements, CRCP IRI, a lot of the sections between 60 and 80 inch per mile, and then you have quite a few between 100 and 160. And now we look at the final distributions, pretty similar, except for a few less data points. Distress surveys, I mean, most of these are between 6 and 14, so that's great. Kind of capture some of the late age IRI. If we look at the model itself with the global coefficients from before, as you have, it's quite good. So it kind of captures the IRI okay. And this is with the updated punch-out coefficients. And even though, I mean, the one item that came out quite well was the residual errors. I mean, there's no consistent bias there, even by base types. R squared is pretty good. Our SCSY is really good. Bias about 3 inch per mile, which is really low. When we look at the p-values, they all failed the null hypothesis, but when we look at the practical significance of a value of 3 or 4, difference of 4 inches per mile is really low. Similar with the intercept of 9 inches per mile compared to 0. I mean, that's basically, even though they fail, we accept the global coefficients, and the standard error is pretty low. So the same punch-out IRI or the CRCP IRI coefficients from before can be used, but the main item that is updated is your standard deviation for your residual error relationship. So that's the big item that kind of captures some of the variability. Okay, so in summary, we have about 30 minutes left here. Summary, closing comments. I'll just reiterate as a reminder that all the items that I went over today is really only included in version 3, the web application. So that's your new cracking models based on NCHRP 151, recalibration of the global models, inclusion of your MERA 2 climate for default climate data. Now it's one climate data set for both flexible and rigid pavements, and direct MERA 2 climate data download and integration is only included in Pavement Design version 3.0, and that's the web application. Just to reiterate the new inputs, we have our A value, concrete characteristic length, some adjusted built-in curling calibration factors. We did not change these from the recommended values from NCHRP 151. These we didn't need to go into and explain some of those differences. So these were accepted. Same as well with the L star value. We did look at quite a big matrix of values and found that the default parameters recommended by the authors from NCHRP 151 were quite reasonable. So that's why they were selected, and they were, yeah, they were okay. New inputs here, so some of the changes for asphalt base, granular base, and cement treated bases. As I showed earlier, actually, yeah, these I think changed. I think I have these columns flipped. These are correct, new values. They were implemented. We have our calibration coefficients. I'm going to go through these fairly quickly, so it just reiterates what we had. New coefficients for C4 and C5 for JPCP cracking, new standard error or standard deviation or residual error relationship. Faulting, we have a new C1, C3, C6, and C7, and standard deviation of residual error. All new JPCP IRI coefficients and standard error relationship. New CRCP punch-out coefficients, and the CRCP IRI coefficients remain the same, while the standard deviation of the residual error was updated and changed. Lastly, I want to mention that the calibration assistance tool updates, so that's currently getting upgraded to include all the necessary changes for pavement and design version 3.0. That's the new rigid models, updated user guide and manual, plus the JPCP and CRCP LTPP sections and non-LTPP sections that we're using in global calibration. So it'll have the ones for that we use for cracking, faulting IRI, plus for CRCP, the punch outs and IRI. And the expected release is in October, so it's working hard to get that out because I know there is a need for that and to move to version 3.0. Just lastly, I want to acknowledge some people, and they worked really hard to get this done and get this in Pavement ME. I want to thank Dr. Lev Kazanovich and Dr. Alex Gottlieb for all of their valuable feedback and guidance throughout this integration process. I mean, we worked with Lev to make sure that the equations, the source code, and everything is works with what they intended from 151 and fix some of the issues, the typos, and any other equation differences. So that worked out well, and I really want to thank them for their efforts. Then also the Pavement and Design Task Force for their valuable feedback during our meetings. And then also the other team members from ARA. From the software team, Chad Becker, William Rumler led the efforts to transliterate and get the code and the models into Pavement ME, and then Peter Rowe as well for looking at and updating the user interface changes in analysis domain. So I that these people were valuable to get this out and implement it into the version 3. And then also the engineering team. I would like to thank Harold and Praveen for all their efforts and help throughout this. Okay, so last, I want one more poll question, so I'll open that and then I'll turn it over to Clark.
So let me know when you're ready to go, Wouter.
Sounds good. Yeah, I think we'll give it another 30 seconds or so. There's some people still starting the poll that are in progress. Okay, well, I'll close the poll. We'll give whoever started time to finish. Okay, well, thank you for answering those questions, and I'll turn it over to Clark.
Okay, we've had a number of questions. There was one on the availability of the calibration assistance tool updated for version 3, and you mentioned that just right at the end of the webinar. So that's great. I think to recap, we're expecting that in October. And most of the other questions have been addressed by Harold. I don't know if there's some that you'd like to kind of cherry pick to go over now.
Yeah, let me go through them. I haven't looked at all of them yet. I think Harold answered all these.
Yeah, Wouter, you may want to comment on one that, just so that everyone understands, you had summarized the type of pavements, especially the JPCP, on the cement-treated bases, asphalt-treated bases, lime-stabilized bases, and granular bases. But we did have some where the concrete was setting directly on the embankment soils. So
yes, and those were kind of lumped into the ones with granular bases, but we didn't. So when we looked at just those itself, there wasn't a big difference. So they,
no, right, and that's why they were combined into the granular base ones.
Yep.
Okay. There's also, Wouter, one question. I'm gonna. It was in the chat box. And it had to do with, did we evaluate the Pareto coefficient frontiers on JCP faulting verification, ? And I'm not sure about the terms, the definition of the terms here, so I really didn't answer it, other than there was another question on the validation. And we did have, I think you used 80% for calibration of the data set and 20% for validation. I don't know if that's where the question was going, but if you, under the chat box, if you understand Pareto coefficient frontiers, you may want to comment on that.
Yeah, I don't have a specific comment on that. And the other thing for the calibration validation portion, I mean, we look at when we initially split the dowels, well, dowels versus undoweled. We look, that's one way, and not just that, but also the constant joint spacing, random joint spacing. That was another way to kind of verify some of the models can capture some of those portions. Also looked at looking at the kind of a bootstrap sample, just kind of see a distribution of your residual errors with resampling. Basically, after the calibration was done, say with the entire data set or the 80%, basically then subset those sections and calculate SE and residual error. So kind of briefly looked at that as well.
The other comment, just so you may want to comment on, had to do with punch-outs, the number of punch-outs per mile. You know, the statistical parameters, at least some of them, weren't very good, but just, you know, how we determine within a 500-foot section the number of punch-outs per mile when it's only 500 feet.
Yeah, so there's a conversion between your number of punch-outs per the 500 feet to the number of punch-outs per mile. That's basically what we used to get to, punch-outs per mile.
Right. Yeah, I guess the point here is, let's make a point that, and the same thing is true for flexible pavements on transverse cracks, because it's only 500 feet and the program predicts, you know, feet per mile of transverse cracks. And so anytime you do that, the error term is going to go up. And that's the reason for, you know, many of those statistical terms being a lot less, because the assumption that we're making is that 500-foot section is representative of a mile. And it may be, you know, more detrimental or less detrimental to a mile section. And so there's an increased error there that shows up in the statistical variables.
There is a question at the very bottom of the Q&A box that hasn't been addressed. What would be the difference in design thickness using the revised factors in the older version?
I think I did run some examples. I mean, I didn't see the cracking itself. I mean, the design thicknesses weren't that different. Bigger items more at, say, your reliability levels. I think it captures, or the global model specifically, I think you're going to see potentially thicker and thinner pavements. Depends on what level of reliability you're using, but also the traffic level. For cracking, I don't think it's going to be a major difference. Now for faulting, I think, go ahead, Harold.
Well, I was going to say, for the granular bases, the lime treated, and where concrete sets directly on embankment soil, I don't think there's going to be much of a change at all in anything in terms of the thickness. For cracking, there may be for the asphalt stabilized bases as well as the cement stabilized bases. There will be a difference there. I think the one question that has come up external to this webinar is and I think you were about to mention it, on the reliability for IRI. I think correct me if I'm incorrect, but the IRI standard deviation equation is going to be generally lower. And if it's lower than the higher reliability, the users will see a net decrease in concrete thickness compared to the older version, I believe. And, I believe that's correct.
Yeah. No, I think that was the bigger update on, especially for IRI and faulting itself.
Right.
I think we've covered or answered all the questions, I believe. There's another one.
Yeah, Jim Mack sent, I keep scrolling. J4 factor increased dramatically, will have an effect on your northern climates and A7 soils. Yes, it did, but the factor that really impacts your IRI predictions is faulting. So the faulting factor actually reduced quite a bit. So overall, I think it may not have as big of an effect as you might see. I mean, it is something that it has the potential to, but if we look at where's the faulting coefficients? Yeah, cracking is also reduced. So, but the faulting is coefficient here from 1.4929 to 0.99, and that's really what affects your IRI prediction the most. Because even at small faulting levels, so your average faulting is say 0.01, that is multiplied by the total number of joints within your section within a mile to get your average total joint faulting for an IRI in the IRI calculation. So I think it'll kind of even out, but it's something to look at.
And the term, Buder, also the age term, still the exponent to the age term is still 1.0 in the site factor, correct?
Yeah.
Yeah. So as you go, down the road in time, the impact of the site factor on a time basis still remains the same. The relative difference, that exponent is still 1.0. Oh, the other thing too, I guess, related to the site factor, we probably should mention is that NCHRP 159 is completing, and that the task force and the comp committee will review the results, and probably a decision on that will be made sometime next year, or within this fiscal year. And my guess is that that may have an impact on the site factor for both concrete as well as flexible pavements. And I know Claudia Zapata was the PI on that, and she will be making a presentation to the task force in the October meeting on the results and the impact of that NCHRP study, on pavement ME.
Yeah, and another thing to add to Jim's question on the site factor itself, the reliability is I think it's going to be quite a bit less. I mean, if you look at the standard error, residual errors, right, that is a big update there. So I think it's not going to have as big of the site factor is not going to control that as much as it might in the current model. Okay. I haven't seen anything come in after that. Okay. Clark, I'll pass it on to you. Clark.
Okay, thanks. Thanks, Buder. That was very informative. A great job. This, again, was our second webinar of this fiscal year. The first one was on the new web application. And we actually have two webinars that were presented introducing that web application. and they're both available on the ME Design website, me-design.com. This was our second of the fiscal year, and again on NCHRP 1-51 and the rigid pavement global recalibration, and that one will be posted soon, so keep an eye out for that. Next slide. We do have 2 more webinars coming up for this fiscal year. Webinar 3 will be in quarter 3 of the fiscal year, so that's roughly January through March, and webinar 4 will be in the 4th quarter, roughly April through June. We are looking for ideas for topics, and if you have a suggestion, we would love to hear it. And probably the best way to send that in would be through an email directed to pavementmedesign@ara.com, and that goes to the Pavement ME Design Help Desk. Next slide. And we'll end with just some contact information. Ryan Fragapane is our AASHTO project manager, and his contact information is shown, and I'm the chair of the task force, and my email address is presented there as well. A really good resource, if you haven't visited, you should. It's where the webinars are posted after completion, and that's me-design.com. I should point out that we do have a Pavement ME Design Users Group. That's currently being managed by FHWA and Jennifer Albert, and Jennifer's email address is shown. And I would like to mention that we do have the Pavement ME Users Group meeting coming up November 1st through 3rd in Salt Lake City this year. So I would recommend that meeting to everyone who has interest in Pavement ME Design. You can also get information through the help desk. The preferred contact is through an email, pavementmedesign@ara.com, but there's also a phone number given, 217-356-4500. The ARA staff, who do a great job supporting the product, are Chad Becker, Buda Brink, and Harold Von Quintus, and their contact information is also shown. And with that, I'd like to thank everyone for attending.